Hello, everyone, and welcome to today's EAStalk webinar, brought to you by the European Aquaculture Society. My name is Anna Viskovic, and I'm Project and a Program Manager at the EAS, and I will be your host for this session today. Whether you're tuning in as a student, researcher, or industry professional, we are happy to have you with us as we explore another key topic in sustainable aquaculture. Today's session will last 45 minutes with a 30 minutes presentation, followed by 15 minutes live Q&A. So please know that the participants, you can leave your questions in the chat, and we will address as many as possible during the live discussion at the end. As always, this webinar is being recorded, and it will be available on the EAS YouTube channel for 1 month, after which it will be accessible only to the EAS members on our website in the EAStalk webinar archive. So if you are not yet a member, I encourage you to check out our membership options, and free membership is available for students and retirees. Today's webinar will focus on recirculating aquaculture systems, or RAS, and specifically on key water quality parameters that are essential to monitor and control. We will also take a closer look at how MAT Kuling's innovative water treatment technologies contribute to optimal fish welfare and production efficiency. This session will provide a practical overview of RAS design and function, including mechanical filtration, biological treatment, degassing, and ozonation. We will also explore how integrating protein skimming and ozone treatment into a system can help reduce organic loads, improve water clarity, and enhance overall performance. We are also happy to note that MAT Kuling is a corporate member of the EAS, and today's session is being presented as part of their membership benefit. To guide us through this topic, I'm pleased to welcome Nil Llonch Llussà, Regional Sales Manager for Europe, Chile, and Japan, RAS Specialist in Aquaculture Engineering at MAT Kuling, a Norwegian company known for its advanced water treatment technologies for aquaculture. Nil is a trained biologist and aquaculture engineering with extensive experience in design, evaluation, and planning of RAS facilities across Europe. He has worked on feasibility studies and system development for a wide range of species, from salmon and trout to pike perch, sea bass, barramundi, and even soft-shell blue crab. With experience across both engineering and biology, Nil brings a well-rounded perspective on how technology and fish welfare intersect in modern aquaculture systems. So without further delay, let's dive into today's presentation. Nil, the floor is yours. You can start.
Thank you. Thank you for your presentation, Anna. Thank you for inviting us to this talk. And yeah, without further delay, since it was a very accurate presentation, I will start the slides. If you have any problem in listening to me, just let me know. Okay, let me check. All right, so here there's just to start off, I have here a brief presentation of what the company, a little introduction of the company. Sorry, MAT stands for Marine Aquarium Technology. This is a company that was first created for working and providing technology for aquariums. And thereafter, MAT Kuling was created for dealing the aquaculture sector. This is a Norwegian company. Therefore, there it comes the related Norwegian words to this MAT. With that, we have our production facilities in Turkey. However, as I mentioned, the company is Norwegian, and we have offices across Europe and also Middle East. Check. Yeah, so as I just mentioned, we have the production facilities in Turkey. They are located near the city of Izmir, one of the biggest cities in Turkey. We just recently opened up a new facility, and we have yet to have the pictures of this one, while the second one on the list, it's our current production facility. There's a video of the production hall that I'm just starting. And then we have our offices on the third facility, while and in addition to that, we have a fabrication for FRP and acrylics for swimming pools. However, it is not related to our sector. Then, moving on, this is just a very big picture of all different equipment that we produce. I just want to show it. I'm not going to go into detail because it would take too long time, but just show that we produce all different equipment required for recirculating aquaculture systems and treatment, and including tanks and all different details and equipment that could be required. I will briefly mention a few of these units when we move along the presentation and related to the water quality parameters that we will be looking into. So starting the topic, water quality. Understand your fish. So as in this picture is represented, it's very hard to tell how a fish is feeling until it's really struggling for their health and, for example, heavily breathing. And from this moment to becoming dead, it's very short period. Therefore, it's very important to monitor your water quality and to keep your parameters in check. So the different parameters that we need to monitor can have direct effects on the fish's gill tissue. If we look on the pictures here on the right, we can have particles directly damaging the gills, as well as damaging the skin or their fin erosion. This can also be related perhaps to interactions with other fish in the tank. Then other than that, we have direct effects on the gills through toxicity of different compounds or also asphyxia. So fish are not able to breathe properly. And moving on, indirect effects, we can, if the particle concentration in water is too high, it can serve as substrate for bacterial growth. This is something that we want to avoid. Then also we can have increased turbidity of water because of certain compounds. And also because of bacterial growth, we can have higher oxygen demand and CO2 production. And also certain bacteria strains can create or produce off-flavor compounds, which we want to reduce as much as possible in order to reduce the purging time. Also, different compounds that we monitor in water quality can affect the biofilter capacity and efficiency. This leads overall to stress, reduced feed intake, increased oxygen demand of the system as a whole, opportunistic bacterial infections on the fish, and in the end, also increased mortality. So this is a picture that most of you probably already know, but I just want to contextualize where the waste in recirculating aquaculture systems comes from. This is basically the feed that we put into your system. You want to reduce as much as you can the feed waste, so uneaten pellets, in order to be efficient in the feed usage, but also because uneaten feed contributes the most to waste compounds. Then the feed that is consumed by your trout, for example, in this picture, there's a rainbow trout, it's processed, and part of it, of these different nutrients, are excreted, mostly as particulate matter, feces, and there's also some other dissolved substances. In addition, your fish breathes, so it consumes oxygen and produces CO2. Then on the right, we have a list of critical parameters from more to less critical in our systems that we need to monitor. So we have oxygen, total ammonia, nitrogen, ionized ammonia, which is very toxic at low concentrations, so good to keep track, solids, nitrite, CO2, and nitrate, which is the less toxic form of the nitrogen compound, dissolved nitrogen compounds. And to these commonly known parameters, then we have also to add this that is gaining more and more recognition lately, this hydrogen sulfide, especially in saltwater systems that you have higher risk of production because of sulfate availability in your salt water. At very low concentrations can have big mortality effects, but also at even lower concentrations, so above this 1 microgram per liter that I'm mentioning, can have at chronic exposure can have negative effects in growth and also survival of the fish. So looking into our RAS components, I added here a 3D picture of general components that we find in recirculating aquaculture systems. Different systems present most of them. Some systems exclude part of this different equipment, and there's also different configurations in terms of order of how you put each of these equipment. However, in general, we find a mechanical filtration step. It could be a drum filter. Then also you could add your fine filtration step for smaller particles. It could be a protein skimmer. Then you can also have ozone injection, which can be in the skimmer, perhaps. You have biological filtration or treatment through your biological filter. It could be an MBBR, degassing, UV disinfection, temperature control, so through a heat exchanger, and oxygenation. All that is controlled by different types of sensors and automatization. And in addition to that, you add your sensors for water quality control. This can be centralized in a control board and automatized through a PLC. Then the first and most important topic of the water quality that I will be focusing today is the solids treatment. In aquaculture, the nature of the solids comes from, I have highlighted in this picture here on the left with red circles, comes mainly from feces and uneaten feed pellets. However, we also find fragments of the previous, or for example, biofilm of the biofilter or some other surfaces. Then in between, among particles, we can differentiate between bigger and smaller particles. Macroscopic are the particles above 100 microns. These can be settled or filtered easily, while the microscopic particles below 100 microns are harder to remove. However, within this same fraction, we have to differentiate between two different sizes. Above 30 microns, particles that can be filtered by microfiltration equipment, such as drum filters. Below 30 microns, particles that are very hard to remove from your system. And we can perhaps suggestions for treating these particles are media filters or protein skimmers. So, microfiltration. I will introduce drum filters, which is the equipment that we produce for this, for treating these particles above 30 microns. We produce equipment of different sizes and flow rates ranging from 10 to up to 8,000 cubics per hour, and of course different mesh sizes depending on the type of use. Of course, agriculture mesh size, it's always limited or a range below 100 microns meshes. Why using drum filters? It's the most commonly used in aquaculture until now, at least in recirculating systems. So it has a reliable record of performance. It has a reduced footprint compared to other filters. It is simple and reliable. It also has an automatized functioning and cleaning. And this video I will skip. So digging in a little bit on mesh size selection, I will talk about this recent published article from Denmark Technical University from Jesus. He recently presented these results, and well, it was focusing on the test of different drum filter mesh sizes, 30, 45, and 70, in a rainbow trout recirculating aquaculture system setup. And he was testing the differences of these different mesh sizes, how it affects the water quality, and which mesh size is the best, considered the best to select for treating your water. According to his results that I have added and highlighted in this slide, the best results were achieved comparable to the smallest micron mesh. It was achieved at 45 microns. So 45 and 30 microns, as you can see in the different plots, presented different similar results and the best results. Only turbidity was not significantly different to the biggest mesh, 70 microns. However, it was still better result with the smaller micron mesh. So why using 45 instead of 30? With 45, you don't need to dimension the big, you don't need as much surface filtration area for the same amount of flow. So you would require a smaller filter than using a 30 microns mesh. So it would save you costs on your equipment. So it would be smaller equipment. With these 45 microns, he achieved 60% reduction in turbidity, also 60% reduction on particles size between 1 and 180 microns, also 60% reduction on particulate POD, so particulate organic matter, and 50% reduction in microbial activity, which is shown in this last plot where it says H2O2, so hydrogen peroxide degradation rate. It's an indirect measure of bacterial activity. This bacterial activity reduction may not be directly related to the filtration, but maybe since you reduce the particle count on the water, so the suspended solids, it was an indirect effect, so less substrate for bacteria to grow. In any case, also, I have a last remark on this one. Keep in mind that your removal rate will end up depending on your feed type. So feed type depends on the type of fish that you have, and also the size of your fish. So maybe if you use different species, for example, marine species and larvae culture, then you will have a smaller feed use, and you won't have the same results as it was found in this study. Moving on to fine filtration, in this presentation, I will only talk about protein skimming. I will leave media filtration out of this presentation. I just don't have time for it. And also, it's more commonly known, the media filtration itself. So focusing on protein skimmers, how do they work? They have, as you can see in the middle picture, there's a yellow pump. This is an internal recirculation system of water. This pump creates pressure to a venturi, where this venturi creates suction pressure on the air. So air is injected on this pipe, and this pipe, this circulation loop goes to the bottom of the skimmer, where the bubbles are created. You can see in this window, this picture here. The bubbles travel upwards motion while the water is introduced on top. So it's moving both different directions, and the bubbles itself create the foam by interaction with the particles that you have in the water. These fine particles are trapped with the bubbles, with this foam that overflows from the top of the cone, and you create this dirty foam, as you can see in this picture, which is discharged, therefore cleaning your water. We have both fresh and marine water skimmers. They are different, mainly because of the air injection capacity is different. I will look into that later more specifically. I will also comment on removal efficiency and also using skimmers as ozone contact chamber. So why using skimmers? As I was mentioning, to target the particle fraction between 1 and 30 microns. Let me first point out this graphic here on the right. This is a study that checked the particle concentration of different sizes in a control a normal RAS system with a drum filter and a treatment, also a normal RAS with a drum filter, but the treatment, it was spiked with additional amount of particle concentration. In both systems, as you can see, particles below is 30 microns, you have accumulation, so you cannot remove from the system. That's why you need some kind of treatment in order to target these particles, if you want to target them, of course. In addition to getting rid of these particles, the skimmer is also used. There's some systems that produce foam, so you can use the skimmer to get rid of excess foam created in your RAS system. Generally, in RAS systems, foam is not created, is not a problem, because feeds contain certain percentage of fat content, and this fat doesn't allow the proteins to emulsify and create this foam. However, if you have trapped dead fish in your system, it can have leakage of additional protein content into your water, creating foam. Or also in unfed systems, such as purging systems, you can have foam creation. If we look at the picture down to the left, this is a picture from a facility, a degassing basin. So there's air injection into this basin in order to degassify your CO2. Here they have foaming problems. So they had foaming problems in the degassing, and then you have this foam creation, and then it overflows into the floor because you don't have a previous treatment with a skimmer, for example, that you could have collected this foam. Then looking on the other pictures, the remaining ones, it's two pictures from bubble creation in fresh to the left and salt water to the right. So we can see by observation already, naked eye, that the bubbles in the marine water are much smaller and are much more effective at trapping capturing these fine solids in the water, because the relationship or the ratio between surface to volume of each bubble is much higher. Therefore, it has higher contact area to the water and to the particles that are suspended. Then, and also I want to mention that the skimmers are also an adequate reaction tank for ozone. They have kind of a synergistic effect, since ozone helps. There's two methods of action of ozone that can enhance protein skimming performance. One, it's make the dissolved particles not soluble anymore. They have they leave certain parts that are not soluble into water anymore, and therefore these particles trapped into the bubble and are collected upwards. Also, the ozone makes the particles coagulate. That means that they interact with each other, making bigger particles, and are easier to remove afterwards. And also it greatly enhances performance in fresh water, which is limited compared to marine water. And this I will mention afterwards. It also has a direct effect on off-labor compounds removal. Then here there's a lot of information, but I will briefly mention, and I just want to focus basically on the picture of the right. This is also another study from Denmark Technical University, also from Jesus. This is a very visual way to see what's the effect of using skimmers and skimmers plus ozone. So from left to right, we've got it was a trial with rainbow trout, recirculating system. So from left to right, we've got ozone treatment, and we've got ozone plus protein skimming, control, the brown one, and the less brown, it's only protein skimming. This is a freshwater system, I want to punctualize. So the removal or the effect of a skimming was limited compared to marine water. So if we look on the table, we have 3 treatments. I excluded the control here. FF stands for foam fractionation. This is protein skimming. It can also be called like that. Then O3 stands for ozone treatment. And the last one is a combination of both. In general, it can be seen that the ozone treatment alone was better than the foam fractionation alone. But this is, I have to remember, this is fresh water. If it was marine water, maybe it would be comparable in certain aspects or different water quality parameters. And in the end, I also want to remark that the combination of both gives the best results. So if we look at the last column, it's where the highest, yeah, and I didn't mention, sorry, these are the percentages of removal compared to the control one, which is the very brown one control over there. So looking back at the pictures, ozone can remove the color of the water. So both ozone treatments have clear water, and and if we look at the last tank, the one to the right, the color is not removed. However, the particles are partly removed. And if we look at this row where it says turbidity, actually the turbidity, regardless of the color, is lower in the protein skimmer treatment than the ozone. That's because the particle volume removal was higher in the skimmer. So it really has a significant effect on particle removal and turbidity. Then we also conducted 1 month independent test with the third party, the Norwegian Institute of Water Research, NIVA, for our freshwater protein skimmers, for a skimmer that was sold to Mowi. The treatment conditions was a water retention time of 1.5 minutes, so 1 minute 30 seconds. And this treatment it was with ozone injection. In this graphic, we can see the removal percentage of each particle size from 1 micron or 0.8 microns to 30 microns. Overall, the particle removal of the particles in between these sizes, it was average 40 to 50%, let's say, with the best results achieved at 30 microns, which was 60%. The smaller that we get in size, it's harder to remove, even with ozone. But in any case, it doesn't contribute so much to the total solids in water, the very small particles. Then getting into ozone, we have different ozone generators, our different capacities range of ozone generators. We produce our ozone with corona discharge, so with electricity, and they are water cooled. Ozone is a highly oxidating agent used in RAS for direct oxidation of organic matter, dissolved organic matter, and other compounds, including for reduced compounds such as hydrogen sulfide. And it also, as I mentioned before, it has a coagulation effect, so it can help coagulate particles, make bigger particles so are easily removable from the system. It directly oxidates of flavor compounds, so it removes jasmine and MIB, and it also presents disinfection properties. In RAS, it has a recommendation range generally between 15 to 25 grams ozone per kilo feet. It can also be more. In some systems, we've been requesting more. And it's important to control its dosing, wherever you're dosing, with ORP probes. So you're sure controlling how much you're dosing and dose the right amount, because every system has local conditions that you should adapt to. And it's also security to avoid overdosing. So if you're dosing too much ozone, then you have an ORP probe that tells you, hey, you're dosing too much, then you can have an automation to stop your ozone generator. Then as security measures for any not reacted ozone in the water, dissolved in the water, you could add low pressure UVs that are shown that at a dose above 80 millijoules per second per square centimeter can completely remove concentrations below 0.5 milligrams per liter. And also you could add degassing afterwards, also as possible security. Then in saltwater systems, it should also be dosed with more care than in salt water, only because it can interact with these bromide ions and form secondary toxic substances. However, it's very hard to form these substances in low ozone doses that are usually used in RAS, below 1 milligram per liter, since they quickly react with organic matter. So very low possibility to to have these toxic substances created. And in any case, you should have the previously safety measures that I have mentioned above. This is a study that I want to specifically mention about geosmin removal in a commercial facility, Swisslax, that they produce Atlantic salmon. There was evaluation of geosmin concentration in the water. So you can see in this graphic geosmin concentration in the period of time. And where it says start of ozone is where our skimmer plus ozone injection was added. So afterwards, the fluctuation of geosmin grid, it stopped fluctuating and also reduced to very low levels, resulting in low levels of bioaccumulation in their fish. Yeah, and then moving into the last part, I will briefly mention a little bit about nitrification. We produce moving bed reactors, which are very efficient in nitrification because you can add a lot of biomedia, therefore having a reduced a lot of biomedia that it's efficiently mixed. Therefore, you can have a lot of surface area in a very reduced space. So it's space efficient with high nitrification rates. Also, in moving bed reactors, and specifically in our design of moving bed, we have no dead water zones inside, so there's no water matter, no organic matter accumulation, neither the need to clean it itself. I will also mention this a small graphic here. I hope it's possible for you to see. The numbers are not so important. This is a study from two different RAS systems. On the left, we have a RAS system with a fixed bed bioreactor, while on the right, we have a system with a moving bed bioreactor. So they studied the dynamics of hydrogen sulfide production in these two different systems. Excuse me, just 1 second. Let me have some water. And generally, hydrogen sulfide is produced in places where you have high organic matter concentration available and also low oxygen concentration. So generally, in this study, it was seen that hydrogen sulfide was produced in fish tanks because it's where the fish excrete your organic matter and you have higher amount of organic matter available. And then if we compare, that was the green column, and then the blue column shows that this is the main difference that I have highlighted. The fixed bed, it's a producer of hydrogen sulfide, while the moving bed, there's a negative correlation. So since it's always aerated, then you have no production of this toxic compound. And then the red column in both systems, it was a degasser. So it was oxygenated water where there was a negative correlation. Yeah, this is just a video of how the media moves inside the reactor. We have a combination of two different ships in order to boost its capacity as well, two different biocarriers. And the last part of it is just aeration and degassing. I just want to highlight very quickly, because I see that we're running out of time, that this plot here, it just shows percentage of weight gain in different concentrations of CO2 in your system. That I just want to show that the lowest that you keep your CO2, the higher growth coefficient that you will have in your fish. And yeah, we have different types of aeration and degassing equipment. The trickling towers can remove up to 65% of CO2, and generally are cost-efficient solutions for degassing in RAS systems, while we have degassing towers for higher performance. These are much higher. Both equipments are cross-flow air and water injection, so water comes from top and air is ejected on the bottom, and CO2 is exchanged through the media. These degas towers can also have the option for being a cleaning option, so you can clean the media, and also they come in vacuum, so you can, in very high intensive systems, you can have vacuum and have higher degassing performances. And I don't have time for more. I just want to show you quickly different clients that rely on us, and we can move. Well, thank you for listening, and we can move to questions.
Thank you so much, Neil, for informative and practical presentation. You have given us valuable insight into the link between the water quality and the fish welfare, and how thoughtful system design backed by effective treatment technology can improve both sustainability and performance in RAS operation. We will now open the floor for our Q&A session, which is going to be live. So if you have any questions, please type them in the chat box, and we will go through as many as we can in the time we have left. So for this, we have 15 minutes. So let's get started. The first question we got is from Anil Telbusher. What are your experiences with the nitrification reactors or other more specialized type of water treatment like Anamox? Is there any interest from the customers?
So yeah, thank you first for the question. So if we're talking about bacterial compositions of communities, we don't usually work with that. Each client has different ways of starting up the biofilter themselves. Sometimes they use bacterial premixes from certified companies that supply this kind of premixes, while others start up their biofilter some more rudimentary ways. In any case, in most of these production systems, they do not have data about the bacterial composition, so it's hard to tell what's their actual composition. We specifically don't have information about the bacterial composition in our bioreactors. I'm sorry, I cannot dig deeper into this topic.
Thank you, Neil. I would also like to remind you that Neil left his email address here on the last slide. So feel free to mark it down, as well the general email of the MAT Kuling, in case you are feeling a little bit shy, but I hope that's not going to be a case today for the Q&A. But if you want to stay in touch with Neil, feel free to mark his email and get in touch with him after the presentation. So Neil, I'm going to ask you the question from my end. What is your view on skimmer market in aquaculture in the years to come?
So regarding skimmer inclusion into commercial aquaculture systems, it seems to be an increasing trend. There's more and more requests regarding that, especially in high-intensive recirculating systems. Basically, because you want to keep your water quality as best as possible in order to boost your fish growth, decrease turbidity in water, and there's also science and studies that show that fine particles can have negative effects negative effects directly on the gill tissue, which of course afterwards affects this perimeter fish growth that I was mentioning. In addition to that, it's compared to the whole system, it's not a big investment, and having part of the flow at least treated by your skimmer, you will have great results in terms of water quality and clarity. Therefore, I think you can achieve much improvement by adding this type of equipment, and it can also serve as a good contact chamber for ozone because of the contact time, and also because ozone can be collected on the head, so it's easily point of collection of any off-gas ozone that you may have in your system, so not reacted with the water, sorry. Big improvement and an increasing tendency, that's for sure, in both fresh and marine water, we see.
Thank you, Neil. The next question we got is from Pablo Cabo Valraza. In terms of efficiency for a small module, would you choose a fixed or mobile FB in terms of same size?
Can you repeat that one?
Yeah, sure. So in terms of efficiency for a small module, Would you choose a fixed or mobile FB in terms of same size?
By FB, I understand that it means fixed bed. I understand. For a small module, I don't know how small you mean here. I don't know if you're restricted by available space in your location or in your planning and where you're planning your system. Yeah, so if I don't know the sizes that we're talking about, but if it's a quite big, large of FB, I would recommend a fixed one. While if it's small, always modular, it's better as you can move it around or change it position or move it to some other place when needed. If you want to further reduce your footprint, I would recommend MBVR instead of a fixed bed, if that's what you meant by FB. You can, if I didn't understand the question, you can write to me or email me afterwards, and maybe we can look into that specifically.
Thank you, Nil. The next question we got is from Elisa Siropoulou. Thank you for the nice overview. Do you expect other biofiltration technologies like electro-oxidation or chemical oxidation emerging anytime soon? And do you apply nanobubble technology in protein skimmers?
Okay, so 2 questions. All right. So for nitrification, I'll start with the first question. In terms of electro-oxidation of TAN, of total ammonia nitrogen, there seems to be some research done in that. I know that some companies are already offering that in a commercial scale. I know that so far they have succeeded. I don't know how to call it, how feasible is that in terms of operation expenses, because I know that these reactors, for example, are very expensive and they need to reapply the electrodes in a yearly basis, if I'm not wrong. The electrodes are expensive. In addition to that, they have high electricity costs. So I don't know how well is the implementation of this type of technology in commercial systems. But there seems to, along with these companies that offer it, I think there's also some company in Israel that they are bringing up onto the commercial scale. I don't know how far they have reached, neither how well it's operating. In the other question, which is nanobubble technology, nanobubble technology cannot be used in combination of skimmer. Nanobubbles remain in suspension in the water, therefore they do not rise as microbubbles created in the skimmer, and because they don't rise, they cannot be collected with the particles on the head of the skimmer. Nanobubbles are used, as far as I know, with 2 purposes: keep your oxygen level high within all your recirculating system, and also some type of scoring or cleaning of internal piping, but not used. It cannot be used for within skimming, with protein skimming.
Thank you, Nil. The next question, are you finished with answering on this question?
I think yes. I think I didn't forget anything. Yeah.
Okay. So the next question we got is from Masresha Birara Fekadu. Kindly, can you share with us your experience with the relationship between fish diseases and water quality?
Okay. Not easy, because it's very system specific. I will say that because this is it's hard to answer in terms that for example, in RAS systems that I've been working on, there were no disease outbreaks. However, as I was mentioning before, if you maintain poor water quality, it can lead to stress of fish. So if fish are stressed, are more susceptible to diseases. Plus, other parameter in water quality, as I mentioned before, also solids can create some types of damages to gills and skin, making it, for example, lose part of the mucus that it's protective layer of the fish's skin, and making more prone to bacterial communities to settle there. So most of the times you try to maintain a healthy bacterial community in your system. So in theory, you should not have major infections in your fish. But of course, if by any chance your biosecurity is compromised, plus you have your fish stressed or in bad conditions, then you will suffer more. So it's better to keep good water quality. Of course, depending on fish species, there's some fish species that are more resistant to different concentrations of the different water parameters. We could have a long discussion on that one. I don't know if you were referring to some species in specific. You can write to me afterwards. Maybe we can have a specific discussion about that.
Thank you, Nil. I would also like to remind you all that we still have 5 minutes left for the Q&A. So now is the time to write down the questions you might be having for Nil. The next question we got is again from Anil Telbuscher. Following up on Elisa's question, how common is the use of electroagulation or flocculants in general? Is it less cost efficient than protein skimmers?
Okay, so here there's two types of technology that similar but different. We've got electrocoagulation and electrooxidation. Electrocoagulation, it's for treating the particles. So you want to coagulate the particles for them to become bigger and therefore easier to remove from your system. While electrooxidation, which was Elisa asking, it's the oxidation of ammonia reduced compounds from the water. Directly oxidizing these compounds and not related to particle removal. I think Anil was asking about electrocoagulation, if I'm not wrong. Electrocoagulation, as far as I know, it's not common in commercial farms. I know that I don't remember specifically, there's some company offering it. I don't know already if in a commercial setup or not, but the purpose that they are offering it's to perhaps have a higher efficiency on your mechanical treatment step through a microfiltration equipment, such as a drum filter, and maybe getting rid, as you were saying, of this fine polishing skimmer. In terms of capital and operational expenditures, I don't have data, so I cannot directly tell you which one is cheaper, but I assume that the electrocoagulation may be more expensive. As I was mentioning, the electrodes are expensive. They need to be replaced yearly, and the electrical consumption, I assume it's higher than what you could have in a protein skimming, but I cannot say for sure. So maybe someone listening is supplying this technology and can prove me wrong. And I will be glad to have information about that as well.
Thank you, Nil. Can you tell us more about what's the difference between fresh and marine water skimmers? And does protein skimming in fresh water work well?
Yeah. I briefly mentioned about that before. So basically, the difference between our fresh and marine water skimmers is that because of the limited efficiency of, and as compared to marine water of a freshwater skimmer, because the bubbles are bigger, we have a bigger pump for recirculating, and therefore having higher air injection and more bubble creation on the bottom. Therefore, we try to compensate the bubble size of fresh water with more air addition and more bubble formation inside this vessel. And as experience, I can say that freshwater protein skimmers are largely requested and used in commercial setups, but usually and mostly in combination with ozone to have this enhancing effect for foam formation. Since it, as I was mentioning, it helps create particles that are dissolved and soluble and attached to the bubbles, and therefore being removed afterwards.
Thank you. In your opinion, what is the major threat in running a RAS?
Sorry, can you repeat that one?
Yes. What is the major threat in running a RAS?
Yeah, that's a difficult question. Everyone, maybe many people would answer differently. Let's say that you have to know your system well. You have to know how to operate your system well. Have monitoring, like constant monitoring and alarms of your system, and have security. If something goes wrong, what will happen? So always think of the worst case scenario and have solutions for that. That would be my advice. And of course, have operators that are able to cope with any issues or mistakes that may arise during operation.
Thank you, Nil. As we are coming to the end of the Q&A, I have a last question for you.
Yeah.
What is the potential of RAS in the aquaculture sector?
Okay. So yeah, this is just a general question. I will give my own opinion and also what I see. There's an increasing trend of installing RAS, both in larviculture and especially in larviculture, because you want to control your water parameters, your water quality parameters as good as possible in order to increase your survival rates or maximize your survival rates, and also maximize your growth. Also in broodstock in order to control your broodstock spawning. And then, of course, depending on the location that you're in the world, you have more or less water available. So if you have less water available, it's also an option to go for RAS and produce full size of whatever fish that you have in mind for marketing your local market or abroad, of course. Yeah.
Thank you again, Nil and MAT Kuling. I think we're coming to the end of this webinar. For sharing your expertise and supporting this EAStalk webinar. Actually, if you don't mind, Elisa just send us another question before we do the official wrap up. Yeah. What is the CAPEX approximation per kilogram of fish?
The what? Can you repeat the?
CAPEX.
The CAPEX.
CAPEX, yes.
Yeah. Honestly, this is something out of my scope of work. Since we are just the equipment supplier, we do not work in all different operational expenses of the fish farm itself. So I do not have a specific number to tell you in this case. I guess it depends on company to company, depending on different factors such as feed, electricity, and other consumables that they use. Also the price of the fish, if they produce the fish themselves. Not easy to tell, and I think it's a company specific question, a production company specific question.
Thank you, Nil, again. I would also like to thank you all for joining us today. And just as a final reminder that this webinar was recorded and will be available on a YouTube channel of the EAS for 1 month. I will be sending you a following up email by the end of this week. You can also download the presentation on the EAS website under the membership portal. We hope to see you again soon in one of our upcoming EAStalk webinars. And until then, take care, goodbye, and enjoy the holiday season, and Happy New Year from the EAS. And thank you again, Nil, for joining us today and for sharing your expertise.
Yeah. Thank you, everyone. And if someone writes to me, I'll try to answer soon, but it'll probably have to be in January, since Christmas is coming and we're very busy these days. I will try to catch up as soon as possible if there's something. Thanks for listening, and thank you for inviting me.
Yeah, our pleasure. Thank you for accepting the invitation and for presenting amazing webinar today.
Thanks.
Thank you.